Hi, I'm Jay Lee. I'm very pleased today to share with you about Industrial AI and Big Data-enabled resilient industrial system in the post-pandemic era. I will have three topics to cover today. One is a definition and how we define automation, intelligent system, as well as digital system, and as a relationship with the industrial internet. And second, I'd like to introduce the industrial AI approach, how we integrate with industrial big data for future implementation of smart system. Number three, I will give some examples, how we design such a smart, resilient manufacturing system. First, I'd like to talk about Fastcon technology transformation. Fastcon new board was formed 2019. So the new board members set a new strategy in early 2020, and we define as a Fastcon 1.0, Fastcon 2.0, and Fastcon 3.0. Fastcon 1.0 is to evaluate current capabilities to identify the strength and the weaknesses. And of course, we're going to improve the strength and also reduce or eliminate the weaknesses or repair them. Number two is how we accelerate the digital transformation, start impacting our business operation day to day, also how we work with customers, and how we also work with suppliers. Number three is how to create new industries for the next 10, 20 years. We call it Fastcon 3.0. In the Fastcon 3.0 area, we have identified the three potential industries we're going to build. The first is called EV, electrification. Second is called digital health. The third one is the future robotics. Eventually, there are three key technologies, including AI, semiconductors, and also 5G and 6Gs. Together, we call 3+3. So let's look at how we define the automation system, intelligent system, and also digital system, how they connect to future industrial internet as a whole. I often talk about our industrial system using this 4-quadrant thinking. All the system we deal with, industrial system, doesn't matter it's a manufacturing system, robotics, AGVs, and wind turbines, high-speed train, etc. So we have a visible world, we have an invisible world. So for the manufacturing system, of course, the typical thing is the lean manufacturing, called continuous improvements. We experience the problems, we identify the bottlenecks, and we have pains. We will improve them over time continuously. But that is experience-based approach. But it's very hard to continue for next generation. So we need to build a model to predict those things that will happen, to prevent from happening. So we call the model-based approach. This could be a data model, could be a physical model, also could be an operation model. But sometimes those are root causes, those are invisible relationships. We need to use big data to mine them. Once we mine them, we can build a model, integrate with physical model and known knowledge. Eventually, we can avoid those invisible things before they occur. So the blue areas, we're talking about future opportunities for industrial internet that including automation, intelligent system, and digital systems. First, let's define what is an automation system, what is an intelligent system, and what is a digital system. Use one sentence. Automation system is a system that human don't do well or they don't want to do. For example, the dirty, boring, dangerous. You want to use a robot to do the work. Or they don't do well, right? Human cannot repeatedly do the same job in a very high accuracy. Intelligent system is a system we can do human being cannot do. For example, you want people to inspect 100 small holes within 1 second. It's impossible. And digital system is to support people using data to make decisions. Today, most of us using experience to make decisions. But eventually, after decisions made, nobody knew what happened. Nobody can predict the future. Nobody can repeat what you have done, right? So those legacy disappeared. Could be innovation, and could be something, and issues happened. So eventually, when we look at future, how we use the automation system as a source, right? We have many automation systems that have data generated from history. Now, we need to do data to convert to some kind of a useful format we call digitized data. Once the digitized data, we can use AI or machine learning to train the system. Eventually, we can have an intelligent system to make decisions, to avoid problems, or to increase the value of a prediction. And eventually, we create value for customers, create value for suppliers, and those we call the data in closed loop flow from automation system to the value creation. But often we talk about industrial internet, right? Industrial internet, there are three key elements. One is a people. One is a things. So for example, we have a manufacturing system to managing the process parts or quality. And eventually we have a decision support system to make things happen. Could be ERP, could be MES. But the problem is, very often we think the things, for example, a robot or machine, can inform people what's wrong. Is that true? Actually, as they go through a system to inform people. For example, your phone connect to APP can turn the lights on. Or if some lights off, APP can inform you something problem. So eventually, the decision support system could be a different form. Could be APP, could be a modeling, could be a decision making. So for people, it's called internet, connect people. For things, internet of things. For industrial internet, connect to different types decision making systems. From smaller system like a mobile APP, for large system like ERP, like CRM, like POM. So now, how can we look at the industrial AI and what's the role of industrial big data, industrial AI, and to use such a system to improve the performance? Data come from all sources. Could be the machinery, could be manufacturing operations from industrial system. When the data come, we need to train the system. We sometimes use 20% of data, and we use 80% system to train them, to test them. Unfortunately, we don't know the quality of data. Therefore, the data cannot be reused. So first, we have to evaluate, can we use such data to detect the problem happened before? Second, we should evaluate, can we use the same data to detect or to diagnose the problem, the root causes as before? Furthermore, we can predict the problem happened before, to predict if we can repeat the same prediction. So this is a very important part of the data quality and evaluation system before you implement any AI. But when we look at the AI and industrial AI, what is the difference? What's the difference between AI and AI? We can call is a cognitive science. We use cognition, improve our vision, natural language processing, and also robotics, etc. But most of the time, it's a try and error approach. So algorithm developer, scientists develop algorithms based on trial and error approach. For example, today, if I give you two algorithms to two different engineers to use the same set of data to make decisions, you know what? Most of the time, the results are different. This is not acceptable for engineering system, right? So eventually, we need a systematic discipline. So industrial AI is a systematic discipline. So we can, two engineers using same data, same algorithm, the result is the same. And we can repeat the same problems over and over again to evaluate, to train the people. So that's called industrial AI, the big difference between two. So let's compare. We had many expert systems before. We had the AI and industrial AI. What is exactly the difference? As human, we grow our experience over time. When we retire, experience disappeared. So we want to have there's a discontinuity. Other people can learn, but they're different. Expert system we used before is we work with expert to capture those knowledge as a rule. There's a rule-based approach to make decisions. Unfortunately, it depends what type of expert, how good they are. So there's also a gap between two different experts. So AI, machine learning, we train the system, but in the beginning they're unstable, take time to converge. Once they converge, they can start replacing human decision making. Unfortunately, if a system has a major problems or breakdown after maintenance, you have to recalibrate. Sometimes you have to retrain the system for software upgrade. But we have a lot of data generated over the time, over the year, so we could train them continuously. So this is called Inertial AI. We train the system continuously, so even system has a breakdown, they can recover quickly and reposition, recalibrate by itself. This is called Inertial AI. Obviously, there are many different algorithms and techniques we can use to perform fault detection, diagnostics, and prediction. So these algorithms, tools, the different types, different a baseline. But how we select these tools, how we use them systematically, not using try and error approach. There are so many algorithms you can compare. Sometimes we have to use 3 competing algorithms so we can select the best one based on certain issue like sensitivity, time to make decisions, also the noise of data. So very often we have challenges to select the best tool. It depends on what type of algorithms in what situations. So we can make a lookup table to compare, for example, between random forest and the logistic regression. Which method is better? We deal with a very noisy data environment, right? So that's very important to have such a tool. Of course, there are also challenges. For example, we want to make decisions very fast, and we want to make very precise decisions. Well, there's no free lunch. So certainly there's a complexity and uncertainties. Also, we have to evaluate with a trade-off when you make the right decision, select the right tools. But this is on the algorithm side. But how about methodology? For example, you have a great recipe in the kitchen, you have great kitchens, but if you don't know how to cook, recipe doesn't mean anything to you. So we need the right methodology. There are many different methodologies to implement industrial AI. It depends on what type of environment. For example, I have lots of data. Or I don't have data. Or I have a broken data. I have a low quality data. Or I have many machines very similar. Or I have many machines that are different, like jet engines and high-speed train, robots in factories. There are several methodologies, and people can use it and to implement the industrial AI in different industrial systems. But today, this is one example. We call the fleet-based analytics. What's a fleet-based analytics? We have many similar systems out there, like wind turbines, high-speed trains, robots in the factory floor, EV running everywhere. Those are fleet. For example, robots. We have many robots in factories. Do you want to monitor every single one? Probably not, because it will take lots of data collection, lots of network problems, also discontinuity of data from different sources, from old history, from the modern sensors. Well, what we can do is each robot, every day you do 3 minutes test cycles. So by comparing test cycles, you can quickly understand the difference of each robot's performance by clustering them into different type of small clusters. We call divide and conquer approach. By comparing them, we can select the worst one, eventually focus on that one. Just like the teacher give a test to the kids in the classroom. You give 3 different quiz, quickly find out which students are not good one. Right? So rather to examine student every day individually. You don't do that. So this is called the very quick a similarity-based approach to find out which robot has a problem in the factory floor. They're very fast, using a small amount of data to make intelligent decisions. Now let's give an example. How we build the industrial smart resilient system. Resilient means we can avoid things, right, for the potential risks. Let's look around today's manufacturing. Many companies are suffering for finding chips worldwide because of shortage of semiconductor production, and also the demand and supply chain that are imbalanced. During the COVID period, and demand reduced, supply is interrupted. And during the recovery, some cities, some countries, they start growing, then the supply is interrupted. And eventually, the two are not balanced right now. Of course, the transportation logistics between cause big problems. So today, there are many vehicle companies cannot find enough chips to make cars. Of course, there are other industries have similar problems in different ways. So there could be pandemic problems, could be unknown problem, could be natural disaster problems. But how can we build a resilient manufacturing system to prevent, to tolerate such issues? Of course, there could be a issue on logistics, the issue on inconsistent suppliers. Also, issue could be on the capacity of different factories. Also, we can how to prevent impact of a labor shortage and also inconsistent skill sets. If different workers, the work skill different, how can system to tolerate that inconsistency, still reconfigure them to do the right and the high quality products. Also, we want to prevent unknowns, which we don't know what going to be, right? We have different stages of risk management system, like a cyber attack system, for example. In Fastcon 2018, the company made decision trying to capitalize what we have, the physical asset. The company has 175,000 machine tools, 80,000 robots, and 1,800 SMT lines. But if we can harvest the data from these assets, then we can create a very good baseline models for these assets. Eventually, we can build the cloud and also database, also the physical models to predict problems, even provide more services for other worldwide factories. Eventually, the bottom line is to improve the efficiency and reduce the labor cost, also improve the value creation for the customer and suppliers. So 2019, January, the company received the World Economic Forum Lighthouse Factory Award. And such a factory we call the Lights Out Factory. Why Lights Out? We want to challenge the workers. You don't have to worry about the quality. You can just alert system to predict itself, alert you before things become worse. Eventually, you can reduce lots of redundant labors, right? So that's called the competitive factories. So for the last several years, the company has making effort trying to build over 20 lighthouse worldwide. And this year, the company also received a second award for the Chengdu facility. Also, the other 3 sites also receiving awards as well. But the future is, doesn't matter where the factory is, we like to using our big data capabilities to monitor, to operate, to some extent make decisions for all factories from a center place. Could be a central location. You don't have to have every factory of big data. So because of cyberspace, I can manage many things differently. So we call the cyber physical factories. Can connect the physical world and cyber decision world together, right? Then we can manage I can compare similar things worldwide. So in conclusion, we use A, B, C, D, E to conclude. A is AI or analytics. B is big data. C is cloud. And D is domain knowledge. And E is evidence. For industrial AI, D and E is very important. A, B, C, D, E. So D and E, the most important for industrial AI. The reason is we want trained people have skill sets with the domain knowledge, how to evaluate, how to find the data, how to use the data, eventually how to use the right tool and make decisions. So we call 3T model, the talents, technology, and tools. Eventually, those models can use to evaluate the readiness. Where are you today versus where you should be tomorrow? So again, I have a book called Industrial AI, and you're welcome to take a look at it and to use as reference, right? Thank you very much.